Yeah, so today we'd like to talk to you all about two-dimensional vortex interactions as a physical mechanism behind the inverse cascade. And I'd like to tell you how very low-dimensional point vortex configurations, when placed in a background shear, are really good at predicting the outcome of extended vortex interactions in two-dimensional Euler flow. So I'd like to get you all situated with what the inverse cascade is. So I have an example here of a system relaxing to the inverse cascade. On the left, I have a two-dimensional inviscid flow, and I'm showing you the vorticity. So wherever you see red, it's rotating clockwise. Wherever you see blue, it's rotating counterclockwise. On the right, I have the Fourier transform of the energy density. And you can see that I've initialized the flow with a lot of energy content in the intermediate wave numbers. So as we see the system evolve, you'll see that the Fourier transform is going to decay down to the -5/3 scaling that was predicted by Kreischten in 1967. And if you look in real space, you'll see that this relaxation process is really mediated by vortex interactions. Namely, we have pairs that merge. We have bound pairs that sort of advect through the flow and remain in proximity without merging. And then we also have unbound pairs that are ripped apart by external shear. This third case is only possible in the presence of external shear. So any symmetric vortex interaction can basically be described as this configuration. We have two cores of characteristic radius r. They're separated by some length L, and they're embedded in a background flow of strength S. Formally, Euler has an infinite number of conserved quantities. There are two that people like to use when they talk about the macroscopic properties of vortex cores. Namely, there's gamma, which is the integrated vorticity, and there's J, which is the radial moment of the vorticity. These are conserved when you integrate over the entire plane, but people will integrate these over the core itself and consider that a macroscopic property. So these properties allow us to define two non-dimensional parameters. There's lowercase s, which is the ratio of the shear strength to the vortex amplitude. And then there's lowercase l, which is separation distance relative to the vortex core size. The purpose of this talk is really to investigate the parameter space here of s and l and figure out where these boundaries between bound, unbound, and merging pairs exists. And so to really keep control of how many degrees of freedom our vortex cores have, we're going to be taking a point vortex approximation and assume that each core is made up of n point vortices. This is a Hamiltonian system, and in the limit that n gets very large, the dynamics of this system will approximate that of full extended Euler flow. There are other notable reduced order models of vortex cores, namely Anderson and Farsman came up with the Rons model. Melander et al. Used a moment model of vortex cores. Zabuski did a contour dynamics model. And then Roberts and Christensen actually used the same point vortex cloud model that we're using here. They used the limit of very large n. We're going the opposite direction. So we're taking n equals 1 and 2 and seeing just how far we can get in making predictions in this very low dimensional configuration. So n equals 1. We're going to show this already predicts the boundary of unbound pairs. So in this case, you simply have two interacting point vortices. Because we assume that it's symmetric, there's only 2 degrees of freedom, basically the position of one of the point vortices. So we can actually plot the Hamiltonian as a function of one of the point vortex positions. Because energy is conserved, the point vortices have to move along contours of the Hamiltonian. So this is really a phase space picture of what sort of dynamics are accessible in the system. You'll notice that there is a separatrix that I've plotted in bold. Inside the separatrix, the vortex-vortex interaction dominates, and they will simply rotate without each other. Outside of this separatrix, shear dominates, and the two point vortices will be ripped apart. So essentially, the geometry of the separatrix gives us an approximation of the boundary of unbound pairs through the major and minor axis. 2 important points. The orientation of the vortex pair relative to the shear matters, right? That basically tells you if you're along the major axis or the minor axis. Second, merging is not accessible to the system. There are not enough degrees of freedom to show merging. So what's really fascinating is that if we now do a parameter sweep over extended vortex cores, so this is still point clouds, but we're using a lot of point vortices now, and we use a lot of different vortex profiles, such as Gaussian, bump function, and patch profiles, we find that the L major and L minor from the last slide is a good predictor of the boundary between bound and unbound configurations. So what I'm plotting here on the right is the effective radius of the two vortex system as t goes to infinity. So wherever you see red, it means the two cores were ripped apart. And so again, n equals 1 is a very good predictor of this boundary. But it doesn't show merging, right? So in order to show merging, we have to go up to the n equals 2 case, where there are now 2 point vortices in each core. And as soon as we look at this system in the presence of very small background shear, we find that the point vortices are permuted within their own core for some time, and then they begin permuting point vortices in between cores. And this is indicative of the onset of a merger. So how can we understand this process better? Over the past 2 decades, a lot of work has gone into showing how invariant solutions describe turbulence, both in 2 dimensions and 3 dimensions. Solutions such as equilibria, traveling waves, and periodic orbits are good at describing the spatial and temporal evolution of turbulence. So this is no different for the case of vortex merging. A lot of work has gone into computing traveling waves that are relevant to the merging setup, basically. So here, by Chiaratelli and Williamson, they've computed a traveling wave solution and continued it from where the 2 cores are disjoint to where they seem to merge into one blob. There was a lot of hope that the stability properties of this branch would tell us where the merging boundary exists, but there seems to be some discrepancy. Mergers, or it was predicted that mergers should happen at L between 3.1 and 3.5, but Munier found in 2002 that experimentally this happens closer to L equals 4. So there's some sort of discrepancy there. In our system, we have shear, so there's no longer rotational invariance, right? So we no longer expect traveling waves to be relevant. We expect periodic orbits to be the relevant solution. And so we can compute every single periodic orbit in this 4-point vortex system. So we've computed this orange branch here, where point vortices are permuted within their own core. And we've continued that down to where it hits a saddle node bifurcation off of a traveling wave solution that simply just rotates around the origin with no permutations. Off of that, there's another blue branch, which permutes point vortices internally and has 2 satellite vortices on the outside. And there's also this disconnected branch that permutes all point vortices. And so what we can see here, if we look at this chaotic trajectory from before, is that it follows the orange branch. If you can see here, the period is slowly getting longer each revolution, which shows you that you're going along this branch towards the saddle node bifurcation. And then it hops onto the yellow branch and follows that for some time. So it seems that these periodic solutions are really good at describing the merger process for n equals 2. Better still, the location of this traveling wave is pretty indicative of where the merger happens. And we find that that is at 3.86, which is a lot closer to the experimental value than was actually computed for these extended vortex core traveling wave systems. So, in summary, we've shown that very low dimensional point vortex configurations, when placed in a background shear, are good at predicting the outcome of extended vortex core interactions in 2-dimensional turbulence. Future work is going to extend basically this boundary here, so we want to look at the n equals 2 system when placed in a lot stronger shears. We really just looked at the low shear limit. And also we want to add the n equals 3 case, which allows us the extra degree of freedom to look at how profile impacts these outcomes. Munier found that profile was pretty important in the merging boundary, and so we'd love to add that into this analysis as well. Thank you.